To determine the appropriate conductor size for a 100 amp subpanel located 225 feet away from the main service panel with the conductor installed underground in conduit, several factors must be considered, including ampacity, voltage drop, and applicable electrical codes. According to the provided information, a number 4 American wire gauge copper conductor is specified. We need to verify the appropriateness of this conductor size by examining ampacity and voltage drop. Firstly, ampacity refers to the current carrying capacity of a conductor, which is dictated by the National Electrical Code, or NEC, Table 310.15b16 or similar tables. For a 100 amp subpanel, the conductor must have an ampacity of at least 100 amps. According to NEC Table 310.15b16, a number 4 American wire gauge copper conductor with a 75 degrees Celsius insulation rating typically has an ampacity of 85 amps in some older codes, or 95 amps in more modern codes. This ampacity might appear insufficient for a 100 amp load. However, the NEC permits the use of the next highest standard of a current protection device rating in certain situations as per NEC 240.4b. If the conductor ampacity does not correspond exactly to a standard breaker size, you are permitted to use the next size up breaker. Considering this rule, a 100 amp breaker can be used to protect a conductor with a minimum ampacity of 85 or 95 amps. This means the number 4 American wire gauge conductor could be acceptable based on ampacity alone, but always consult the local code. Secondly, voltage drop is an important consideration, especially over long distances like the 225-foot run in question. Excessive voltage drop can cause appliances and equipment to operate inefficiently, overheat, or even fail prematurely. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. Feeder is the supply to a subpanel, and voltage drop can be calculated using the following formula. Voltage drop equals 2 times the length of the conductor times the current times the impedance divided by 1000. A length is the one-way distance of the wire, which is 225 feet in this case. The current is the load on the circuit, which is 100 amps. The impedance is the resistance per unit length of the wire. For number 4 American wire gauge copper conductor, a typical impedance value is approximately 0.249 ohms per 1000 feet. Plugging these values into the formula, voltage drop equals 2 times 225 feet times 100 amps times 0.249 ohms divided by 1000. Voltage drop equals 11.205 volts. To determine the percentage voltage drop, divide the voltage drop by the supply voltage, which is typically 120 volts for a single-phase system, and then multiply by 100. Percentage voltage drop equals 11.205 volts divided by 120 volts times 100. Percentage voltage drop equals 9.34%. This voltage drop of 9.34% exceeds the recommended maximum of 5% for feeders, indicating that a number 4 American wire gauge conductor might not be adequate due to voltage drop considerations. To mitigate excessive voltage drop, a larger conductor size may be necessary. For example, a number 2 American wire gauge copper conductor has a lower impedance than a number 4 American wire gauge copper conductor and would result in less voltage drop. Recalculating the voltage drop with number 2 American wire gauge conductor. For number 2 American wire gauge copper conductor, a typical impedance value is approximately 0.156 ohms per 1000 feet. Plugging these values into the formula, voltage drop equals 2 times 225 feet times 100 amps times 0.156 ohms divided by 1000. Voltage drop equals 7.2 volts. To determine the percentage voltage drop, divide the voltage drop by the supply voltage, which is typically 120 volts for a single-phase system, and then multiply by 100. Percentage voltage drop equals 7.2 volts divided by 120 volts times 100. Percentage voltage drop equals 5.85%. This voltage drop of 5.85% still exceeds the recommended maximum of 5% for feeders, indicating that a number 2 American wire gauge conductor might not be adequate due to voltage drop considerations. To mitigate excessive voltage drop, a larger conductor size may be necessary. For example, a number 1 American wire gauge copper conductor has a lower impedance than a number 2 American wire gauge copper conductor and would result in less voltage drop. We're calculating the voltage drop with number 1 American wire gauge conductor. For number 1 American wire gauge copper conductor, a typical impedance value is approximately 0.124 ohms per 1000 feet. Plugging these values into the formula, voltage drop equals 2 times 225 feet times 100 amps times 0.124 ohms divided by 1000. Voltage drop equals 5.58 volts. To determine the percentage voltage drop, divide the voltage drop by the supply voltage, which is typically 120 volts for a single-phase system, and then multiply by 100. Percentage voltage drop equals 5.58 volts divided by 120 volts times 100. Percentage voltage drop equals 4.65%. This voltage drop of 4.65% is less than the recommended maximum of 5% for feeders, indicating that a number 1 American wire gauge conductor might be adequate. Thirdly, conductor type and insulation are important. When installing conductors underground and conduit, conductors must be suitable for wet locations. Types such as THWN or XHHW are commonly used for this purpose. The insulation temperature rating must also be considered, as this affects the conductor's ampacity. The 75 degrees Celsius ampacity column is typically used unless the termination points are only rated for 60 degrees Celsius, in which case the 60 degrees Celsius column must be used. Fourthly, conduit fill calculations need to be performed to ensure that the selected conduit size can accommodate the number of conductors being installed. The NEC specifies the maximum percentage of conduit cross-sectional area that can be occupied by conductors. These calculations depend on the number of conductors in the conduit, their sizes, and the type of conduit being used. For example, using THWN conductors, a 1-inch conduit is likely sufficient for 3 number 1 American wire gauge conductors. But calculations should be performed to make sure it meets NEC code. Fifthly, ground fault protection should be considered. The NEC requires ground fault protection for equipment in many electrical installations. The size of the equipment grounding conductor must be determined in accordance with NEC Table 250.122, based on the size of the overcurrent protection device. For a 100 amp overcurrent device, a number 8 American wire gauge copper conductor is typically required as the equipment grounding conductor. Sixthly, local codes and regulations always supersede the NEC, so it is important to check with the local electrical inspector or authority having jurisdiction to ensure compliance with all applicable codes and regulations. Local codes may have more stringent requirements for conductor sizing or voltage drop. Seventhly, neutral conductor sizing must be considered. A neutral conductor must be sized to carry the maximum unbalanced load. In most residential applications, the neutral conductor is permitted to be smaller than the ungrounded conductors, but it must still be sized appropriately to handle the expected load. For a 100 amp subpanel, a number 4 American wire gauge copper conductor is typically sufficient for the neutral. Eighthly, aluminum conductors can be used instead of copper conductors, but aluminum conductors have a lower ampacity than copper conductors of the same size, so a larger size aluminum conductor is typically required to carry the same amount of current. For example, a number 2 American wire gauge aluminum conductor has approximately the same ampacity as a number 4 American wire gauge copper conductor. Ninthly, dirting factors must be considered. If multiple conductors are installed in the same conduit, or if the conductors are exposed to high ambient temperatures, the ampacity of the conductors must be derated in accordance with NEC Table 310.15b3. Derating factors reduce the allowable ampacity of the conductors, so a larger conductor size may be required. Tenthly, future load considerations should be taken into account. It is always a good idea to size the conductors for the expected future load, rather than just the current load. This will avoid the need to replace the conductors in the future if the load increases. The NEC also requires that feeders be sized to carry at least 125% of the continuous load. To summarize, based on the information provided and the calculations performed, a number 4 American wire gauge copper conductor may not be adequate for a 100 amp subpanel located 225 feet away from the main service panel, due to voltage drop considerations. A larger conductor size, such as a number 1 American wire gauge copper conductor, may be necessary to keep the voltage drop within acceptable limits. Other factors, such as conductor type, insulation, conduit fill, and local codes must also be considered when selecting the appropriate conductor size. Always consult with a qualified electrician or electrical engineer to ensure that the electrical installation is safe and compliant with all applicable codes and regulations. This is particularly important given the potential safety hazards associated with electricity and the importance of ensuring the reliability and longevity of the electrical system. Remember that electrical work should only be performed by qualified individuals who have the necessary training, experience, and tools to do the job safely and correctly. Improperly installed electrical wiring can create a fire hazard or electrocution hazard. In addition to the factors mentioned above, it is also important to consider the type of load that will be served by the subpanel. If the subpanel will be serving primarily resistive loads such as lighting and heating, the voltage drop will be more pronounced than if the subpanel will be serving primarily inductive loads such as motors. This is because inductive loads tend to have a power factor that is less than 1, which means that the current lags behind the voltage. This lagging current can exacerbate voltage drop. Furthermore, it is important to consider the harmonic content of the load. Harmonic currents can cause additional voltage drop and can also overheat conductors and equipment. If the load is expected to have a high harmonic content, it may be necessary to use a larger conductor size or to install harmonic filters. When selecting a conductor size, it is always a good idea to err on the side of caution. A slightly larger conductor size will provide a margin of safety and will help to ensure that the electrical system will perform reliably for many years to come. Finally, it is important to document all of the calculations and decisions that were made during the conductor sizing process. This documentation will be helpful for future reference and will also be useful if the electrical installation is ever inspected by an electrical inspector. The documentation should include the following information: the load calculation for the subpanel, the conductor size that was selected, the voltage drop calculation, the conduit fill calculation, the type of conductor that was used, the insulation temperature rating of the conductor, and the ampacity of the conductor. By following these guidelines, you can ensure that the conductors for your 100 amp subpanel are properly sized and that the electrical installation is safe and compliant with all the applicable codes and regulations. Remember that electricity is dangerous, and it is important to take all necessary precautions to protect yourself and others from harm. Always consult with a qualified electrician or electrical engineer if you have any questions or concerns about electrical safety.